Okay. So let me first. Mhm. And so what I thought is maybe it would be a good idea to have a revision kind of class where we summarize all that we have been doing all throughout the course before we have the last class, that is tomorrow. So tomorrow we will be having a class which will be on, you know, antenna and like all that. But before that, what we'll try to do today is uh, is a revision class where we'll try to go through in a very concise manner all the major concepts that we had discussed all throughout the course. Okay, so this class is a part of a TA sheet that I'm doing as a TA requirement for PMRF, and I'm here. I'm doing my PhD here at IISc. So just to introduce myself, I think you already know that. Like, but anyways, so let's get started. And here we will gradually, in this course, we started from electrostatics to magnetostatics to understanding electric and magnetic behavior of matter. Okay, so how one defines permeability, permittivity, how do they affect, transmission of waves through them, polarization of materials. So we discussed all of that. We did discuss all the derivations that lead us to the Maxwell's equations. And then we also talked about transmission and propagation of electromagnetic waves, about transmission lines and waveguides and all of that, right? So today we'll start with our very, well-known, this is where we started. So in nature, we do have this different kinds of forces, right? So there can be strong forces, electromagnetic forces, weak forces, or gravitational forces. And what we saw is that the strong forces or the weak forces, they are very short range forces. Okay. And in our day to day lives, they are not very evident. Okay. On the other hand, electrostatic and gravitational forces are long range. And gravitational forces generally become very evident when we work with massive objects like, what do I say? Celestial bodies and all of that. But for our regular day-to-day phenomena, it's the electromagnetic forces which are very, very prominent and very, very common in our like. We have different phenomena that demonstrates the presence of electromagnetic forces in our lives, right? So initially, when we started, like when this very concept of electricity and magnetism started, that it started as entirely separate subjects. And while that's what we also did in this course, that we gradually understood how this gap between these two, initially separate subjects narrowed down, and finally it became a single subject called electromagnetism, right? So we had this field formulation which talks about action at a distance. So if you have a collection of charges or if you have some current distributions, how will the electric or magnetic field be around them? So you can this very concept of field and how, rather than direct, there's even if there's no direct contact between objects, there can be forces that one can experience because of the other in and it can be, what do I say, explained in terms of this interaction and what mediates that interaction. There comes the concept of field. Okay, so we'll talk about how one can characterize and find fields, electric and magnetic fields, around different charge distributions or different current distributions. And we have already discussed, like as we proceeded in the course. So we started with electrostatics, where you have a finite, like a very static distribution of charges. It can be either discrete or continuous. And then we gradually, went towards cases where there's time variation, things are varying with time, and then how these two effects, like electric fields and magnetic fields, how they, they're intertwined and how they affect each other. So that's how we proceeded in the course, and that's what we'll also do today as a revision. Okay. And we know that, the very concept of electromagnetic radiation is very important. So when you have charges which are accelerating, they radiate, and so they carry energy or momentum with themselves. And then when they radiate it, how this energy propagates. Okay, so that happens in the form of a radiation, and that is what is called electromagnetic radiation. And later tomorrow, when we do the, when we will be going for the, detailed description of antenna and all that, we'll see how this, the very idea of, uh, I mean, accelerated charges producing radiation will be dealt with in greater details. And we'll see what is the effect of, retarded potentials and all of that as we proceed. So that is something which we'll discuss tomorrow. But today, what we'll be talking about is the other things that we had discussed so far. Okay. I think I'm probably about the list. Check once. Uh, yes. Yes. Yeah. So okay. Uh, So we started with electrostatics, where we said that if you have a single charge or a combination of charges, distributed in a discrete way, or you have a line charge or a surface of charges or a region with a volume charge, right? So in all those cases, we have this Coulomb's law, which tells us that if you now bring another charge near this distribution at a certain distance from the distribution, what will be the force that this charge will experience, right? That's the Coulomb's law. So for a single charge, this is how it looks like. It has this 1 by r square dependence. And if you talk about, you know, continuous distribution, suppose if you have a line charge, then this will be modified with this integral, right? You write your charge distribution as integration of lambda dl, or for a surface charge, you write it as sigma dA while you integrate over the surface. Or for volume charges, you can integrate over the volume where your charges are present. And if the so this rho here is the volume charge density. So rho d tau will be the net charge. Okay. So you can do this volume integral to find the net force, right? And then force per unit, test charge will be your electric field. So if you find the force and then divide by the test charge, like Q points at whatever you're talking about, so the force per unit charge will then be defined as your electric field at that point. Okay? And electric field does satisfy the superposition principle, so you can actually add the effects of all the different charges that you have. And this was the very start of our, work course, where we actually tried to explicitly do this integrations and find the electric fields. But then as we proceeded, we saw that if there's a proper symmetry in the system, we can make use of the symmetry. There are even simpler ways of finding electric fields. Okay. So that is associated with this law called the Gauss's law, which is based, or which is, which deals with this very concept of flux. So when you have a field, you can associate field lines with it, right? Which is a measure of how the fields are directed, what is the intensity, right? So these arrows point at the field directions, and the lens also give us a measure of the strength. Okay, the density of the field lines tell us about how intense the field is. So now when you have a field, and if you have some surface, okay, and then there are these field lines that is crossing the surface, so there one can define the flux of the electric field through the surface as this surface integral, which is given as E dot dA. Right. Now, what we saw and what was interesting is that so if you have some region and you have some charge outside, what would happen is the field lines starting from this charge will pass through this region, right? So there'll be equal amount of flux going into the region and equal amount of flux going out. So the net flux that is associated with this region would be zero. So there'll be no net flux. So in that case, what was seen is that the field in this region is not affected by what charge you have here outside. However, if you have a region, so this is something, what we discussed in quite details when we, like very early in the course, that so if you have some region and now if you have charges outside, so it will, all the flux lines will, pass through the surfaces. So the net flux will not be associated with it will be zero, right? But now if you have something inside, okay, so then there'll be a net flux that will be associated with the surface enclosing this region. Okay, so this net flux, okay, can be, so you can do this integral. Okay, if you just put a point charge inside and try to do an integral over the surface, okay, E dot dA, you'll see that it depends on the charge that is enclosed in surface. Okay, and this relation, so this is in the integral form, is called the Gauss's law. And now what we had seen is that by using this relation, we can, in many cases, solve for the electric fields in quite simpler way rather than doing long integrations, right? So this became a very handy way of finding fields in situations where you have symmetry in the system, where you can take the electric field maybe out of the integral and just take a small area element and then compare the left and the right hand side, understanding what is the charge enclosed in that region and all that, right? So we did solve a lot of questions that made use of the Gauss's law. Okay. So now this is the integral form. You can also write it in the differential form. Okay. For this, we use, so there are this theorems like the divergence theorem or Stokes theorems, which are very useful when we talk about vector algebra, and vector algebra is very widely used all throughout the electromagnetism. The study of electromagnetism is integrally linked to understanding vector algebra and using vector algebra. So here we use this theorem called the divergence theorem, which relates a surface integral to a volume integral. Okay, and by using this, you can actually go from the integral version to the differential version of Gauss's law. Okay, so that's what was done. So you can have write the enclosed charge as integration of rho d tau, compare the two. So this would in a way give you, so as you can see, this is in the differential form because you're doing derivatives of electric field, right? Divergence of E is given as rho by epsilon naught, and it's the first Maxwell equation. Okay, so that's how Gauss's law led us to the first Maxwell equation that tells us that if we know the charge distribution in a region, if we know the charge enclosed in a region, we can actually find the electric field. Okay, by using this relation. Now, you know that for to define, factorize any vector quantity, we do need the divergence to be specified and the curl to be specified. Right. So this law here gives us a measure of the divergence of the electric field. Okay. So there were many such questions where, if the electric field is given, if you want to know the charge density or vice versa, we can use this relation to solve for such kind of questions. So there were many questions that one can do based on the Gauss's law. Okay. So that was about divergence of electric field. Now there was, so in order to completely characterize the field that we have, we also need to have an information about the curl of the electric field. So for this, what was done is that if you know that if you have a point charge, this is the field. So what we try to do is we try to do a line integral of the field from some point A to point B, and then we considered a closed path. That means you come back, like if you start from A, you come back to A. That's your entire path for which you want to do your line integral. And in this in the limit of the electrostatics where things are not changing with time, okay, so there what was seen is if you do this integral, okay, for a closed path, it turns out to be zero. Okay. And if you use Stokes theorem, which relates the line integral with the surface integral. So if you have a line integral, okay, and if you have a closed line that makes a surface, right? That encloses a surface. So the line integral over a closed path can be associated with the surface integral of the surface that it encloses by the Stokes theorem. Okay. So using that, what we would do is we should write that for electrostatics where things is not changing with time, we can write curl of E as 0. Okay. So this made our electric field, conservative. And from here, we could define this very idea of electric potential. Okay, that was very useful because now, so because in the electrostatic limit you have curl of E going to 0, you can write the electric field as minus divergence of minus gradient of V, where V is now a scalar quantity. Okay, so that made our very understanding and interpretations or quantifying um, fields quite easier because it's always easy to deal with scalars rather than vectors, right? So you can all for any given distribution of charge, you can always try to first find the scalar potential and then use this relation to find the electric field. That's a much easier way of finding fields rather than looking at individual components and doing the integrations and like doing the calculations with the vector quantities. Okay, so that led to this very idea of electrostatic, like electric potential, V. Okay, so now we know the divergence and we also know the curl for the electrostatic case. So that defines how fields are. In any particular distribution, we can use this relation to find the electric field at a given location. Okay. Now, using this relation, one can rewrite the Maxwell's equation, okay, which takes up this form. Okay, this is called the Poisson equation, and in a way, you can also write, write the Poisson's equation. Like if you put rho to 0, like for a region where there is no charge, you can put in rho going to 0, which gives you that divergence of V goes to 0. So this is called the Laplace equation. Okay, and the solutions to Laplace equations are called harmonic functions. And what we saw is that harmonic functions have very interesting properties. Okay, and from there, this like the properties of harmonic functions led to this very idea of uniqueness theorem and image charges. Again, was very useful when we wanted to, find fields and potentials around, you know, different kinds of charge distribution. Okay, so we'll talk about it, but this is how we finally reach to the same the first Maxwell equation, which relates the divergence of electric field to the charge distribution that can be written in terms of the potential, which gives you this form. Okay, that's where V equal to minus rho by epsilon naught, and when there is no charge, no volume part, rho goes to that is the Laplace equation. So now we did solve for Laplace equation in 2D and 3D and based on the different, boundary conditions, we saw how to do it. So I'll briefly discuss about it as we proceed. So this is how we reach to these major relations that can relate the charge distribution like rho to electric field and then to potential and vice versa, like all these different relations. So if you know one, you can find the others. Okay. So this was about, the very start of, Coulomb's law and Gauss's law and that. And then we moved towards understanding conductors. So that was a it's a very important point that for conductors, because you have free charges, there are very interesting properties associated with what happens when you put a conductor in an electric field. Okay. So you know that if you have any, in electric field, and if you put a charge there, so it would experience a force. Okay. So now, because in a conductor you have many free charges, so one can, very well understand that if you have an applied field, the free charges inside the conductor will experience forces and try to redistribute. Okay. Now, what was interesting is that this redistribution happened quite instantaneously. And what resulted from this redistribution is that inside the conductor, we get an equal and opposite electric field, okay, which is equal and opposite to the applied electric field. That results in a net zero field inside the conductor. So whenever you have a conductor in an electric field, okay, there are electric fields surrounding the conductor, the net field inside the conductor, the bulk of the conductor, will go to zero, okay, because of this redistribution. Okay. And then from Gauss's law, we saw that if rho goes to zero, we can say that the electric field goes to zero, so there are no charges inside. So one can understand that all the free charges, therefore, resides on the surface. They arrange themselves on the surface, okay, such that the conductor becomes a equipotential surface. Okay. What it means is that this, if you move from point A to point B, there'll be no work done. Okay. Or if you move from point A to point B on the surface of a conductor, there'll be no work done because the potential is the same everywhere on the surface. Okay. That also hints at the fact that any electric field at the surface should be perpendicular to the surface. There should not be any tangential component. Okay. So these were some of the interesting features that came up when we talked about what happens when you have conductors um, in applied electric field, and how this, induced charges and like this redistribution results in a net zero field inside the conductor. Okay. And there were very interesting applications of this, okay, which has huge implications. And one of them is the fact that, you can use this feature, this characteristics of conductors, to shield a region from, unnecessary or unwanted themes. Okay. So we did solve several questions which showed that, so if you have a region, okay, suppose this region, and you want to shield this region from any field that is there in the outer region here. So what you can do is you can enclose this region with a conductor. What will happen is that in the bulk of the conductor, the field go to zero, whatever be the field outside. Okay. There'll be redistribution of charges such that the field here inside the bulk of the conductor goes to zero, which results in the fact that now if you change so if you bring in new charges here, change the charge distributions in this outer region, it will have no effect on what field you have inside. Okay, inside. So if you have a cavity inside a conductor, that will be isolated. Okay. So that was something which we had solved. And we did see that, there were this kind of questions where something like this, right? Where we saw that the charge, the surface charge density on the surface, on this, like in the inner surface of this cavities, or the fields in these regions, are not affected by what field or what charges you have here or what changes you do on the outside region. It is even not affected by the fact that you have no charges here. So even if you bring new charge here, that will change the field here, but it will not change the field in this cavity. So these cavities are very much isolated from the surrounding region because of the presence of this conductor, right? So this kind of shielding can be achieved by, surrounding a region with conductors, covering it with a conducting layer. Okay. So then there were some interesting, or important points that, when you have fields and when you go from one region to another, and if there's some interface, then there are certain boundary conditions that need to be satisfied at the interface. Okay. And that depends on what is the charge distribution and like how, and that also comes from, you know, so the very well known this divergence curve, this of the electric fields, and later also for magnetic fields. So they tell us that how the components of electric fields or magnetic fields has to be at an interface. Okay. So suppose if you have a sheet of, some surface charge density sigma. So from this Gauss's law, you can very well tell that the so if there's a non-zero surface charge density sigma here, then the, you know, perpendicular components E above and E below are discontinuous, and the discontinuity is given as sigma by epsilon naught. Okay, so you can use a, consider a pillbox and like use the Gauss's law to get to this boundary condition. While the parallel components, like the tangential components to the surface, okay, because your, curl of E is zero. So for the electrostatic case, we know that curl of E is zero. So that means the line integral of E dot dl will be zero. So using that, you can say that the parallel components of the electric field on this, charge sheet will always be continuous. So E above and E below, the parallel components will be equal. And from here, you can actually use the electric field to find the charge density. Suppose the electric field is specified, okay, then you can use this relation to find the charge density that you have on the surface. If the potential is specified, you know how electric field and potential are related, right? In the electrostatic limit, we know that E is equal to minus grad V. So that led us to this relation. So that means if you know the potential, you can use this relation to find the charge density on the surface. Okay. So these were the different boundary conditions that came up from the equations. Okay. Now, for a conductor, we did see that, if you put a conductor in an electric field, the net field inside the conductor goes to zero because of redistribution of charges, and the charges, like this induction that is happening, and they reorganize such that the net field goes to zero. And it's happening because you have a lot of free charges inside a conductor, right? Now, what happens when you put a dielectric in an electric field? Okay. So even there, you can understand that there'll be redistribution of charges. If you just consider, if you start with a neutral atom, if you just put an atom in an electric field, you know that there'll be redistribution of, so the electron cloud will redistribute. So if your electric field is directed in this way, you can understand that, all the positive, like the negative charges of the electrons will try to move to this end, right? So, and you will have a net positive charge here and a net negative charge here. So you can understand that your atom will get polarized. So similarly, now if you have some material, okay, so all the atoms in this material will gradually get polarized. So there will be a net polarization per unit volume in the material. Okay, and in the linear limit, you can consider that the polarization or the dipole moment that is getting induced is proportional to the electric field that is there. Okay, so this polarization is what is called the atomic polarizability. Now, uh, if you quantify this, polarization as, the dipole moment per unit volume, that is what we called as this capital P, as you can see, right? So there can be many dipoles. It's if you have a region, some dielectric with some region, there'll be many atoms, they'll all get polarized, okay, and that would result in a net polarization per unit volume, which is termed as P. Okay. In the linear limit, this P will be proportional to the electric field that is present. Now, because of this polarization, you can understand that the polarization will also result in a net field. So while you can have free charges, which can result in a field, there can also be, this kind of induced, or bound charges that can also result in a net field. So polarization or a polarized object can also result in a net potential or a field. Okay. So for that, what we saw is that This is the expression for a typical dipole P. Because if you have a dipole P and if you want to find what is the potential at a distance r from the dipole, we know this is the relation, right? Now, if you consider a region of a, like if you consider a polarized region, polarized object where the dipole moment per unit volume is given as capital P, then you can try to find the total potential for the polarized object as doing this integration, right? So you can do an integration of P d tau over the entire volume. And then we did do this kind of reorganizations. So these are just mathematics where we are trying to write it in a more simplified form by using different properties of vector algebra. So when you do that, you this the what the result that you get at the end, okay, that this is very interesting. So this tells us that the potential, the electric potential that generates from you know, a polarized object can be written as the potential that comes because of a surface charge. Okay, so as you can see here, this is a typical expression of a potential for a surface charge where the surface charge is given as P dot n cap. Okay, and there is a contribution of a volume charge where the volume charge is given as minus divergence of P. Okay, so that means if you have a polarized object with a net dipole, net polarization capital P, then the potential due to this polarized object can be written as a sum of potential due to a surface charge, where the surface charge is given as P dot n cap, and a volume charge, where the volume charge is given as minus divergence of P. Now, this charges that is getting generated, like the surface charge or the volume charge, these are not something that you have, these are not free charges that you have externally applied, right? These are generated because of the properties of the medium, because of the organizations inside the medium, inside the object. So these are bound charges. Okay. So now, if you want to redefine, so if you want to find the expression of a Gauss's law in the presence of dielectrics, you can rewrite the total charge distribution as sum of two charges. One is the bound charge density, and then you have the free charge density. So suppose if you put in some charge at a certain location, that's the free charge. But the induced charges that is getting, or induced dipole moments that is getting generated because of this field will also have its own effect on the field. Okay. So that induced or bound charge uh, density will be given as rho b. Okay, so the net rho is given as rho b plus rho f, and accordingly one can modify the Gauss's law. And what we saw is that so now for a dielectric where there is a net, you can consider a net polarization capital P. You can write, so this end you have this epsilon naught divergence of E. Here, this is your total rho, where it has contributions from the bound charges, which is given by this term here, and then you have free charge density. Okay. Now, by rearranging, you get this expression here, which tells us that now you have a new term, which is called the electric displacement. Okay. So the electric displacement is given as epsilon naught E plus P. So this term, the electric displacement, as you can see, it has contributions of, so like you're looking at all of it. So here, like, I mean, inherently, when you consider E, this E is the total field, right? It's the total field. It has contribution of free charges as well as the bound. And then you're also explicitly looking electric displacement is associated with the free charge that you have. Okay. So suppose if you know what is the free charge density, you can directly find the electric displacement. But in order to find the net field, you need to know the medium property. You need to know the polarization that is there. Okay. So now any particular medium in the linear limit, if you consider that the electric susceptibility is given as chi E, so then if you consider that the polarization is proportional to electric field, then you can define this proportionality as the electric susceptibility and rewrite this term. Okay. So then what you find is that in the linear regime, what happens is d, that is electric displacement, which is associated with the free charges, is related to or is proportional to the total field, okay, E, which has effect of both the bound and the free charge. And this proportionality constant is the permittivity of the material. Okay. Now, if you know see how different, like if you do the ratio of this permittivity of the material to the permittivity of free space, that gives you the relative permittivity or the dielectric. Okay, so in many cases we define the we whenever we have a dielectric, we characterize the dielectric in terms of the dielectric constant. So that tells us how the polarization, how much the polarization will be. Okay, so the very information of the electric susceptibility or the polarizability of the material lies in the dielectric constant. Okay, so this gives us a measure of, suppose if you have some applied electric field or some free charge, what will be the bound charge, what will be the net charge. Okay, so that information comes from, so that information needs to consider the effect of the material, how the material responds to the applied field, and that material property is defined as the dielectric constant. Okay, so then we did solve for Laplace equation. Okay, so we saw that there are interesting properties of Laplace equation, solutions to Laplace equation. So any solution to any harmonic function. So all the solutions to Laplace equations are called harmonic functions, and harmonic functions are basically averages of the values that are around them. So if you have a 1D system, then then if your potential is satisfying the Laplace equation, then the potential will actually be an average of the points around plus a and minus a, like that, right? If you have a 2D distribution, so suppose the potential in a region, so there what you can do is you can try to find what is the average of the potential. So any potential at a point will be an average of the potential of the points around it, like of the average potential of the region surrounding it. Okay, similarly for a three-dimensional distribution you can write it as something like this. So so the Laplace equation is a kind of averaging instruction, and because of that, this also tells us this Laplace equation tolerates no local maxima or minima. Okay, so extreme values of the solutions to Laplace equation should always occur at the endpoints, at the surface. Okay, and this also led to this very important theorem called the uniqueness theorem, which will be which we had discussed, as you can remember, and that also had huge implications in simplifying many of our uh, understanding and quantifying the peaks and all that. So it had huge implications there. So in order to solve for Laplace equation, if you remember, we did use the separation of variables, right? So for a two dimension, we started with a two dimension. We also did some questions for three dimensions. But for two dimensions, what we had seen is like this is how typically a Laplace equation would look like. And then whenever you have to find the potential and solve for the Laplace equation, we first started with specifying, looking at the question and trying to see what is the information that is provided so that we set the boundary conditions. Okay. Now, once we know the boundary condition, we took a very simplified, form of the potential where we wrote the potential as product of, functions of x and y for two dimension. For three dimension, you write it as product of three functions of x, y, and z, right? And then we use this very idea of separation of variables such that you have this individual terms which just depends on one variables at a time, right? And in order for this to always work, we saw that you can actually now decouple these two variables and write individual equations for each of them. Okay. And for simplicity, we took these constants to be, k square and minus k square because that simplified our way of, uh, you know, our calculations. As you can see, it gives you a more simplified form of the solution. And from there, you could basically write an expression for the function of x and the function of y. Okay, so this is the general. So you can just look at this, and this is the most general form of your like two-dimensional vector potential using Cartesian coordinates. Okay, so this is how it would look like. Now, once you have this, what we did is now we started applying our boundary conditions. Okay, now based on the boundary conditions, we tried to find the coefficients and also the possible values of your kx and ky, like the wave vectors, like what is the possible value of k. So we did find that from the boundary conditions and also the coefficients. Okay, so I'm not going into the details because this had already been discussed, but we are trying to look at, get an overall idea about how to do it. So once you put in the boundary conditions, you get the possible values of k, and you also get an expression for like some of the, like you simplify for some of the coefficients. Okay, so in a way, if you know this, you can use the separation of variables to tell that the most general solution will be a superposition of all such possible solutions, right? Now you apply the final boundary condition, which you have this condition here, which tells us that at certain point the potential is specified as V naught or something. So then you apply that again. Okay, and at this point you have to use the Fourier trick, which makes use of the fact that when you are writing, like when your solutions like involve this orthogonal functions. Okay, and like, so you have the sinusoidal functions which make up a set of, like, what do I say, set of orthogonal complete set, right? So for such kind of functions, what you can do is what Fourier theorem tells us, that we can write any function in terms of linear superposition of such kind of complete orthogonal set. And this orthogonal sets, they have a orthogonality relation, which tells us that under certain conditions, if you multiply some uh, you know mhm, so out of a set, orthogonal means that it would, if you multiply, suppose sine n pi y by a with sine n prime pi y by a, then when they're equal, only in that case you would have a non-zero value. Okay, otherwise it will always be zero. So they're orthogonal to each other. So when you have already written your potential in terms of such uh, you know complete orthogonal set of functions, so you can use the Fourier trick. Okay, and that will give you the value of this Cn coefficients. Okay, now once you know the expression for Cn, you actually know the expression for your potentials. Okay, so this is your, like, if you have to solve for this question, this would be your solution, right? Now for based on different questions, your boundary conditions would vary. Or if it is in three dimension, then you have to have x, y, and z. So there you'll have, in at this point, you would have to, so here you have k square minus k square, there you have to include another variable so that you can account for three variables, right? So then the constants will be something like k square l square and then minus k square or minus l square, something like that. So you bring in another l there. Why? Because you have to account for three constants, which again satisfy this relation. You would have a 1 by z del square z del z square kind of term here, right? So that's how one can solve for Laplace equations. So using that, what we saw is that now once you know, suppose the potential, right? So if you know the like there's a conductor at a constant potential, V naught. Now you want to find the charge density. So suppose, like in this question, you have found the expression for V naught, you want to find what is the charge density here. So for that case, how we did those questions is we used our idea of, the relations that we found from the boundary conditions, right? So if you know V, we know that this is the relation that relates the potential to the charge density, right? And from there, you can actually find the charge density at that position on the strip. Okay. So that's how one can solve for this thing. So this relation came from the boundary conditions that we had discussed, right? Here, as you can see. So we did discuss all that. Now, Now, in many cases, we did also solve for spherical coordinates, because now when you have, in spherical coordinates, if you want to write the Laplace equation, it would be written in terms of r, theta, and phi, right? And then if you have azimuthal symmetry, you can get rid of this term here. So this is how it would look like. So again, you have to take your potential as a product of two functions, one of r and another of theta, and then use your separation of variables to get individual, decoupled uh, equations for r and for theta. Okay. Now this here, okay, this the solution to this equations are Legendre polynomials, and they're also orthogonal, and they also form a complete set. So they have their own, orthogonality relation, which is again used in the Fourier trick to find the coefficients. Okay. So the solutions to this is the Legendre polynomials. They can be defined by using this Rodriguez formula. So this is how it looks like for different sum of the values. Okay. And the radial part has a form like this. Okay, this is the general form. Now, based on what your question is, you have to choose the functional form of your radial part such that this part remains defined. It does not blow up. Okay, what I mean is, so based on, suppose if you have some spherical region, you want to find the field there. Now, based on whether you suppose you have some sphere or something, right? Now, based on whether you want to find the field inside or outside, you have to choose your expression accordingly such that the radial part remains defined. Okay. So that's why what I mean is, suppose if you are given a question where you want to find the potential inside a sphere. Okay. So in that case, you can understand that inside a sphere, if your R value can go to zero, and if your R value goes to zero, this term will blow up, right? So for finding the potential inside a sphere, your radial part should have a form of a r to the power L. So there, the general form of the potential will look like this. Okay, and then you go ahead with using the Fourier trick, like using the boundary conditions and then the Fourier trick. Okay, to find the coefficients. That is similar to what we had done before, right? But now, if you're asked to find the potential outside the sphere, so then you can understand that like if you look at the general expression, if it is outside some sphere, then your R value, if it goes to infinity, then your first term will blow up, right? So that means for finding the potential in a region which is not bounded, like you know that your R value can go to infinity. So there you have to just have this term, right? So there the general form of your potential will look like this. And then the other processes remain the same. Okay. So you use the boundary conditions, use the Fourier trick to find the coefficients. Okay. And we did solve different questions where, suppose if the potential is given, you can actually write the potential in terms of the Legendre polynomials. Okay. And compare it with your given form, okay, the general most form, and then find the coefficients from there. So once you know the coefficients, you can actually also try to write the write an expression for the potential in a at any particular location, in like the general expression of potential you can define. You can also find the fields from there. So all these things can be done. Okay, so regarding Laplace equation, what we had done is that we started with solving it based on the boundary conditions, find the solution for V, and once you know V, now you can use the relation between electric field and potential, E equal to minus grad V in the and then like that's the thing in the electrostatic limit. So you can just directly use that relation to find the electric field. Okay, now suppose if you know the electric field or if you know the potential, you can also use those values to find the surface charge density. So all these things are related, and we did solve different questions that made use of these relations, right? Okay. Now this very principle of or the very property of the harmonic functions that they allow no maxima or minima. Okay, so all maximum and minimum values should be at the endpoints. So that led to this very important theorem called the uniqueness theorem, which tells us that if you have a region, okay, some volume which is enclosed by a surface, and if the potential is specified on the surface, okay, then the potential inside the volume is uniquely determined. It's a unique value, okay, unique quantity. So that means if you have a region and if you know the potential on the surface, or if you can mimic a situation where the potential on the surface remains the same, but is a much simplified distribution, then the field or the potential that will find inside, like in the volume, will be same for both the cases, right? It is only the potential at the surface that is important to be know. Like if that is specified, you can find the potential inside the volume, and that is a unique quantity, a unique solution. Okay. So from there came this very idea of method of images, right? Where what was done is that suppose you have some, suppose the potential here at a surface is known, and suppose for the simplified case, this is what we started with, okay, just to give you the flavor and remind you. So if you have a region, okay, so some surface, okay, and you know that the potential here is zero, okay, and you know that at a very far distance from this point charge also the potential will go to zero. So basically you know what is the potential in the surface that encloses this, upper like region. Like, so now the question is that what is the potential in this region? Like at different points, what is the potential? So you can understand that in like if you have such region or some surface with a net V potential, you actually don't know how the charges are distributed here, right? You just know that the potential here is zero. So it's difficult to solve for the potential at other regions with just this information, right? But now what uniqueness theorem tells us that if you can mimic this situation with a charge distribution such that the boundary conditions remain the same. I mean, if the potential was zero in this plane, and if you can mimic a condition where again the potential is zero in this plane, and like very far from the charge, the potential still goes to zero. So all the boundary conditions enclosing that region, the surface, if those are the same, but if you have a much simplified charge distribution, they will also result in the same potential, the same field. Okay. So because of which, what we could do is that we could replace this. So we know that if you remove this, like, remove this zero potential surface, but rather replace it with a minus q charge. So again, this minus q charge will, and like the plus and the minus q together will make the potential on the, like in the xy plane, go to zero. Okay. Very far from the charge, again, the potential will go to zero. So that means the boundary conditions are the same for this and for this. So that means now if we can solve for the electric field for this distribution and try to find what is the potential at this upper plane, it will be same as what we would get for this case, right? Now, because this is a very simple discrete distribution of charge, we can very easily find the potential, right? So this is how it would look like direct. So once you know the potential, you can also use it to find sigma. So if you know the potential at this point, suppose, and like how the potential is changing all along this region, you can use this to find what is the charge, what is the charge distribution on the plane that you initially had. So you can use that. Or if you want to find the total induced charge. So if you do this, what would happen is the total induced charge will be equal and opposite to the charge that you have initially, like the free charge that you had here, right? But as you can understand, this was a difficult, complicated situation. This is a much easier distribution in order to calculate the potentials or the fields. Or you can also find the force. So suppose if you are asked what is the force that this charge is experiencing because of the presence of this, equipotential surface, like V0 surface, right? So what you can do is you can replace this with this minus q charge and then try to find what is the force that it is experiencing because of the minus q charge, and the situations are still the same, right? So all the properties would be same. The only thing that would be different is the work done, because in for this distribution, the only work done is in bringing this one Q charge. While here the work done involves bringing two charges, one plus Q and one minus Q, right? So work done for the first case will be half of what you will be doing here. Okay. But otherwise, all like if you want to find fields or potentials and all of that, those will be the same for both the cases. Okay. So in this way, you can use the method of images to simplify your uh, estimations of field and potentials. So this is a very standard question where for a sphere where you have a you know point charge q situated at some fixed distance from the center of a grounded sphere. So you know that the potential on the surface of the sphere is zero. So now what is the potential outside the sphere? So you want to find what is the potential here, right? So again, you can replace this, the grounded conducting sphere and all of that with a charge such that, some charge somewhere here, which is q prime at a distance some b distance from the center, such that again the potential on like in this plane goes to zero. Okay. And like these are the typical results that come out of the calculation. So now if you know this is just a discrete system of charges. So now you can very easily find the potential at some given point, some location, right? R. You can also find the force that one experiences, like what is the force that is experienced by the plus Q charge. So you can also find that it's just given by this relation. Now, it is important to note that if you're asked to find the potential in this region, you cannot bring image charges in the region of interest, right? Because you are trying to mimic the situation, so you can do changes or you can make distributions such that the boundary conditions remain the same, while the region of interest, so the volume where you want to find your fields or potentials, that should not be altered. Okay. So if any particular case, if you are making a distribution of image charges, your image charge should not be in the region of interest. It should be outside that. So here your region of interest is outside the sphere. So you cannot bring an image charge outside the sphere. You have to bring the image charge somewhere inside. Okay. So because if you bring in new charges in the region of interest, that means you are tweaking with the original situation, right? Which is not the case that we want to do. We just want to mimic the question or the situation given to us with some simpler distribution of charges such that the boundary conditions or the potential at the surface enclosing that region remains the same as the one specified to us. Okay. Okay. So that was about electrostatics. And then we did the same for magnetostatics as well. So for constant stationary charge, like stationary charges, we had this constant electric field, and that was the regime of electrostatics. And then we saw that if you now have steady currents, okay, and then that will result in constant magnetic fields. So that's the regime of magnetostatics. Now there is this well-known, this Biot-Savart's law that tells us that if you have a current carrying element, what is the field that this current carrying element will generate at a certain given point r from it, right? And using that, we could actually derive an expression for, suppose if you have an infinite, this is a very standard result, which tells us that if you have an infinite current carrying wire, what is the field, that magnetic field that generates around it? And we did see that it just depends on the perpendicular distance from the wire, right? And this is the relation. So you have this 1 by s dependence. Okay. Now, just as we had Gauss's law from the Coulomb's law, you can have Ampere's law from the Biot-Savart's law, right? Which again makes use of the symmetry and gives us a, a, a simplified version of the Biot-Savart's law. Now, we did see that, like, just as if you have a charge and then if you have an electric field, we know that the charge would experience a force which is given as q into e, right? Now when you have a moving charge in a magnetic field, it also experiences a force, and that force is given as q into v cross b. So the total force in a presence of electric and magnetic field is given as QE plus Q into V cross P, which is your Lorentz force, right? Now, as the magnetic force is perpendicular to the velocity of the charge, so it's perpendicular to that. So that tells us that magnetic forces do not do any work, right? So in like whenever there's a work done because of some electromagnetic field, you have to understand that the work is being done because of the presence of some electric fields associated with it. Okay, so magnetic forces are perpendicular to the motion of the charges, so they do not do any work. Okay, now that means if you now have some, so from here, what you can define is, so if you have a current carrying wire, so a current carrying wire is nothing but a region where charge is moving, right? Charges are flowing. So now if you bring a current carrying wire in presence of some magnetic field, okay, then this charges will also experience a force, right? So in a way that if you have one wire, this wire can result in a field around it, and then when you bring a second wire magnetic field, like second current carrying wire close to it, that would experience a force. And based on the direction of your currents, you can have attractive forces or repulsive forces, right? Now this expression of magnetic force is given by this relation, as you can see here, right? So if you have some current carrying wire where the current is given as I, and then the magnetic field in that region is given as P, then I into dl cross B would give you the magnetic force that will be experienced by this current carrying wire. Now this magnetic force is now based on, if you suppose have a surface current, so you can redefine the surface current as sigma into V. Sigma is the surface charge density and V is the velocity of your charges, right? So so that means like if you have a surface where current is flowing, you can just divide it into such small segments where K can be written as di by dl perpendicular, where dl perpendicular is this small length segment in which you can divide your entire surface, right? So then the magnetic force would be given as something like this. So K cross B dA. So it's a surface integral. Similarly, for a you know volume current, you can define volume current density, which is given as rho into V. Rho is the surface current density, surface charge density, and then you multiply by the velocity of your charges. So that gives you the surface current density. So similarly, you can now divide, like break your volume into small elements. Okay, then the volume current density will be defined by this relation here, and this is how your magnetic forces would look like, right? Now the magnetic forces are very useful in the sense that led to this very idea of EMF and motional EMF and magnetic induction. All these are associated with uh, this fact that there are these forces that can um arise from the magnetic charges moving in magnetic fields. Now, and there are also many other applications. Now, the very idea of charges moving in a magnetic field and the associated forces that they experience is associated with the concept of motional EMF, and from there came this very idea of magnetic flux and how changes of magnetic flux can be related to the EMF or the associated electric field that it might generate. Okay, so that's how the connection between electric and magnetic field started. Okay, we'll just come to that. But for now, till now, what we have discussed is like magnetostatics and electrostatics. So this is like Gauss's law, and this comes from the fact that the line integral is path independent in the electrostatic limit. Then there are no magnetic monopoles, which give us the divergence of B goes to zero. And this comes from the Ampere's law, which is just analogous to how we got to Gauss's law from Coulomb's law. Ampere's law is something which we get from the Biot-Savart's law, right? Now, using this, what we can do is we can, you know, we ultimately want to find electric field or magnetic field or things like that, right? And we are looking for simpler ways of finding these quantities. So we know that it's easier to deal with scalar potentials, and that's why we did introduce this scalar potential V in electrostatics. Right now, there can be a vector potential that can be defined in magnetostatics, where the magnetic field is given as curl of A, where A is your vector potential. Okay, and then so these become very useful. Like here, if you can see, if you use the Ampere's law, okay, which tells us that curl of B should be equal to mu naught J. Now you can use the well-known vector algebra, identities to rewrite this term. Now, because our like the physical quantities of interest is the fields, right? The electrical, the magnetic fields. The potentials by itself can vary by some referential quantity such. So if suppose if your electric field, you know you can always add some quantities to the electric potential such that the field does not change, right? So it's the field that actually matters. So now based on like if we can tweak or add certain quantities to our potential, basically putting in new reference points, right? New ways of what do I say? So just as you can always set a certain value of potential to go to zero, right? That it doesn't matter. So you can always add a constant quantity to your potential. It doesn't change the electric field that we are talking about, and that the electric field is something that we want to find. So based on our like in order to ease our calculations, we can always tweak with our potentials. Okay, so that keeping in mind that the fields should not change because of such changes. Okay, so now that means that if you have a, you can add certain quantities to a such that our equations become simplified, but the net field does not change. So that gives us this liberty of eliminating the divergence of a, because if you choose a which is divergence less, okay, by adding some quantity like this, some gradient of lambda, where lambda is some, you know, scalar quantity, then we know that curl of gradient of any scalar quantity is always zero. So that means this term, this new term that you have added to your vector potential will not change your magnetic field, right? But you can add this such that the divergence of your vector potential goes to zero, and that gives you a very simplified equation. Okay, so that means if initially your original potential was a naught, you can add a divergence of lambda to it such that you get a new vector potential a, which is divergence less. Okay, now for that condition, what we have to do is, so divergence of a should go to zero, right? So that tells us that what your lambda should be. Your lambda should satisfy this condition, right? So from there, you can see that if you know A naught, your original potential, okay, you can add a lambda, which satisfies this condition, which would make your new potential divergence less, right? Now, once your potential becomes divergence less, that means you can use this condition, okay? And this is a much simplified equation. As you can see, it's like the Poisson's equation. So here you can again use it to find. So that means from here you can write A in terms of the volume current density by this relation. So now this is a very like much simpler than solving this, right? So now if you know J, you can use this relation to find A, right? Now once you know A, you can find B. Okay. So all this kind of modifications can be done to your scalar potentials in order to simplify your calculations. Okay. Now, just as in case of electric fields, we had these boundary conditions for the normal and the tangential components, right? So for a charge, uh, surface charge sigma on a surface, we know that the perpendicular components are discontinuous for the electric field, and it's given as E above minus E below equal to sigma by epsilon naught, while the tangential components of electric field are continuous. And you can relate the charge density to the potential or the field by these relations, right? So similarly, now for magnetic fields also you can have you can use this Maxwell's equation, divergence of B going to zero, which tells us that if you again consider a small pill box and look at how the apply this condition to the top surface and the bottom surface of the pill box, this would tell you that the perpendicular components of magnetic fields are always continuous, while now the tangential components depend on what charge current density you have. So if you have a region where there is a current density, suppose some surface current density K, then the perpendicular components will still be continuous, but the parallel components will be discontinuous and it will be given by mu naught K. So it's mu naught because we're still talking about free space. If you talk about some other medium with some different permeability, right? So there you'd change, the mu naught will change to mu. There is the permeability of that media. We'll talk about permeability as we proceed. Okay. So that means till now we know about Coulomb's law, how we went from Coulomb's law to Gauss's law. We know Biot-Savart's law, and then how we went to Ampere's law. Okay, and we know about the definition of scalar potentials and vector potentials and how that can be related to the electric and the magnetic fields. Okay, now if you have some distribution of charges or some distribution of currents, so there you can so so in a specific, like, this is how it looks like, right? This is your expression of your vector potential. So you have this 1 by r terms. Now you can always expand these terms to look at, so now based on how far you are from your charge distributions, there can be, you can write this 1 by r as a, as a, what do I say, as a power series, and then look at what are the dominant terms or what are the main terms that are contributing. Okay, so that will again simplify our calculations. So 1 by r, so if you have some current distribution, and we know that the distance from the current element to your field point is r. So you have to, so in order to find the vector potential, suppose you need this 1 by r term. Okay, now directly finding 1 by r, or doing this integration which involves this term, can be difficult, right? So what you can do is you can write it in terms of a power series which involves this, again, the Legendre polynomials. Okay, so then what happens is, so suppose if you have this, line element, like the current element along flowing along a line. So then this is your expression of vector potential for a current loop, right? So you can expand this 1 by r in terms of this, Legendre polynomials. Like this is a multiple expansion, which gives you individual terms now. Okay. So now you can solve for the individual terms, which is much easier to, integrate and solve. Okay, and then you can look for what are the dominant terms there. Okay, so suppose, like, for the first case, because there are no magnetic monopoles, so the first term will always be zero. So for a, you know total vector displacement around a closed loop, this will go to zero. Okay, this comes from the fact that divergence of B is always zero. So then the next term is your dipole term. Okay, so now this is your dipole term. You can rewrite it to get this expression. So this is a very important result which tells us how the vector potential looks for a magnetic dipole. Okay. So now if you know the expression of vector potential for a magnetic dipole, you can use it, just do a curl of A to find the field due to a magnetic dipole. Okay. So this is how it looks like. This is the field due to a magnetic dipole. Okay. And because the magnetic monopoles do not exist, because the monopole term is always zero, so the magnetic dipole moment, okay, it is independent of the choice of origin. Okay, for the electric charge distribution, whenever the total charge goes to zero, whenever the monopole term goes to zero, in that situation, your electric dipole moment does not depend on the origin. Otherwise it depends, right? But because for the magnetic dipole, moment is always independent of choice of origin, because the monopole term is always zero for magnetic field. Okay, so this is how uh, the magnetic field for a dipole looks like. Okay, for electric field also we do have a similar form. Okay, so now when you, just as we had, polarization for a, like when you had a material in an electric field, we saw that there can be polarization that can arise, and because of which you have a net dipole moment per unit volume. So similarly here, for for a medium, there can be magnetic dipole moment per unit volume, which is called the magnetization of your material. So based on what material you're talking about, okay, based on the material property, okay, just as for electric field we had the susceptibility coming in, okay, the permittivity coming in. So here also we have the permeability, or which tells about how the material responds to the applied field. Okay, so there are different kinds of materials that one can have. So if you have a diamagnetic material, so then uh, what would happen is, when there is no external field, there is no net dipole moment. But once you switch on or apply an external magnetic field, then the moments inside, moments meaning, so there can be small current loops that can form in your material. Okay, just as you can have free charges moving, so you can have like you can have charges moving in a dielectric, you can also have small current loops generated in your material, right? So each of these current loops are individual dipole moments. Okay, so when you apply external magnetic field for a diamagnetic material, these moments align in a direction opposite to the field. Okay, because of which the net field inside a diamagnetic material is reduced, is less than what you have outside. Okay, and if there is no external magnetic field, then there is no field inside your magnetic diamagnetic material. Okay, while for a paramagnetic case, what happens is that if there is no magnetic field, no external magnetic field, then the moments are all like they are they are randomly oriented. Okay, and the net moment goes to zero. But once you apply an external magnetic field, then these moments, the small loops inside your material, they align in the direction of the applied field. So in a paramagnetic material, in presence of an applied field, the field lines get concentrated into the paramagnetic material. So the strength of the magnetic field inside the material is more. Okay, and for a ferromagnetic material, what happens is they always have a net dipole moment. Okay, so there's a net magnetic magnetization always there, even if there is no magnetic external magnetic field, there is a net magnetization in the material. And when you apply a magnetic field, they align towards the magnetic uh, applied magnetic field. So here the magnetic fields are quite intense, and they're like, if you look at the field lines, they'll be very concentrated into the ferromagnetic material in presence of an applied field. Okay, so the net B inside a ferromagnetic material will be much greater than the applied field H. Okay, so that means based on the different materials, on the how the dipole moments are distributed and how they respond to the fields, there can be different net fields that can generate in different materials. Okay, and this can be quantified in terms of the permeability of your material. Okay, so why this is happening is because, just as for a polarized object there was a field that was getting generated because of the polarized object, here the magnetized objects will also have a net field associated with it, right? So if you consider that the vector potential of a single dipole looks like this is something we just discussed. So now if you have a region with a dipole moment per unit volume given as capital M, you can find the total vector potential for your magnetized object by this relation. Okay, and then there can be different simplifications, mathematical simplifications that one can do. The final result is very interesting. It tells us again that the vector potential for you know a magnetized object can be written as sum of two contributions. One is a volume current, which is given as JB, which is curl of M, where M is your magnetization of the material, and another is a potential due to a surface current, where surface current is given as M cross N cap. Okay, so just as we had bound charges for a polarized object. Here you have bound currents for a magnetized object. Okay. Now, based on this fields that generate because of this bound currents, that is what changes the effective field that you have when you put this object in a applied external field. Okay. So now if you want to write the Ampere's law for magnetized materials, you can write J as JB plus JF, where JB is your bound current and JF is your free current. Okay. So again, the bound current is associated with the magnetization. Okay. While B here has contributions from both free and bound currents. Okay. So you can rewrite and get this term here. So here H is associated only with the free current. Okay. So suppose if you have a region and you say that, okay, I have applied current I to this wire. So the current that you are externally applying. Okay. So that's the free current. Okay. But now, based on the material that is around, if the material gets magnetized and if that results in a net bound current, like some J, that would be bound current. Okay. And that will change the effective field, net B, that you have. Okay. So you just as initially you wrote Ampere's law in terms of B, you can also write Ampere's law in terms of H. Okay. So where then the current involved is the free current. Okay. Now, for the linear medium, where you can consider the magnetization to be proportional to the applied field, you can rewrite this term such that you can say that the net field is proportional to the applied field, and this proportionality constant is your permeability, mu. Okay. Now, we did solve for questions like this. So suppose if you have a copper rod with some radius and the current that is there, okay, uniformly distributed current I. So now it's asked what is the H inside and outside. So you can directly use this relation to find the auxiliary field. Okay, auxiliary field is associated only with the free current. So you can directly use the Ampere's law to solve for H, right? But now if you want to find the net field, in that case, you need to know the medium properties. So if you want to find the field in free space, you can always use this relation because you know the permeability of free space given as mu naught. If there's some other medium there, then you need to know the permeability of that medium, or you need to know the magnetization of that medium. Same thing. Okay. So if you know that information, only then you can find the net field. Okay. In free space, if you know H, you can find B by just multiplying it with the permeability of free space. But otherwise, you need to know the medium property, the medium permeability. Okay. And again, based on the boundary conditions, you can use the Maxwell's relations to find the boundary conditions, which are given by these relations here, right? The parallel components have this discontinuity, while the perpendicular components are always continuous. Now we saw that, the very fact of, if you have moving charges and they experience force, and there can be redistribution because of this force, okay, that can again result in a net field. So that very idea led to this concept of electromotive force or EMF. Okay. So in a way, so if you have a circuit, what is the work done in moving unit charge in the circuit? And that's the measure of the EMF of your circuit. Okay. So this very idea of motional EMF came from the fact that, if you have a current carrying loop in a magnetic field, and then now you're moving the loop. So such that the net magnetic field, or, the flux associated with this loop is changing. Okay. So if that happens, then what was found is there is a EMF that gets generated. Okay. So that means, you're moving a closed loop with some velocity v, and because so it's a conducting loop. Okay. And as you are moving, so there are free charges that are moving, and there is a magnetic field, so it would experience some force, and that would result in a redistribution such that there is a EMF that is getting generated, and that EMF would result in a induced current in the loop. Okay. So what was found is that this EMF is associated with the flux that is linked with the loop. Okay, it's given as the negative of the rate of change of flux. So that is what is called the motional EMF. Okay, so we saw that if you have some, current carrying wire I with some magnetic field, right, and then you had a loop. So if you move the loop parallel to the wire, then you know that because your magnetic field is only a function of the perpendicular distance, right? So if you move this loop parallel to the wire, then the net flux linked does not change. And so there is no net, EMF that is generated. While if you move the loop in this direction, in the perpendicular direction, then the flux linked to the loop would change because the field is a function of this perpendicular distance, right? So the net field associated with the loop will change, and that would result in a net EMF that would be generated. Okay. So we did solve different questions that made use of this fact that how the flux linked, the magnetic flux linked to a closed loop can actually result in a net EMF or a net electric field, right? So so these were some very typical questions that we solved, but it is that this concept, okay, which led to the concept of electromagnetic induction, and this lies at the heart of how electric and magnetic fields actually got like connected to each other, okay, intertwined with each other. So what was seen is that it's not basically the motion of the charge, like explicitly you're moving the loop or you're moving the magnetic field region, but it does not depend on that motion, but it actually depends on the relative motion, because the relative motion between the magnetic region and the loop is associated with a change in the magnetic flux that is linked. Okay, so it's the magnetic flux that the change in the magnetic flux that results in the net EMF. Now, what is EMF? EMF is associated with some potential differences, right? So this potential difference means that it is resulting in some electric field. Okay, so this led to the fact that a changing magnetic field can induce a electric field. Okay, so this modified our initial equation of curl of E. So in the electrostatic limit we had curl of E going to 0, right? But then what we saw here is that now if your magnetic field, if you are in a region where your magnetic field is changing, or the area linked to your magnetic field is changing, basically if your magnetic flux is changing, right? So in that case there'll be a electric field that would get generated. Okay, so changing electric field, okay, minus del B del T would result in a electric field, and which would satisfy this condition. Okay, so this led to another Maxwell's equations. So, okay, so this is one of the Maxwell's equations which now related electric and magnetic fields. Okay, this is a very important point. Changing magnetic field can induce electric field. Okay. So before Maxwell, this like till now we have reached to all these equations, right? Gauss's law. This came from the fact that there are no magnetic monopoles. This came from this magnetic induction, and this was from the Biot-Savart's Ampere's law, right? Ampere's law, which was derived from Biot-Savart's law. But what was seen is that there's something wrong with the last law, and what was that is we know that divergence of curl of E, a curl of any vector quantity, should always go to 0. So for the third case, it is consistent because divergence of B is always 0. So this will always go to 0. But for the fourth case, for you know divergence of curl of B to go to 0 always implies that your divergence of J should always be 0. But there is no you know particular reason for us to consider that your J will always be divergenceless. For a magnetostatic case, yes. But what happens when we are not in the magnetostatic regime? There, your J can have a net non-zero divergence, right? So there, the identity will not be satisfied. So that led to the fact that this last equation needs some modification. Okay, and that's what Maxwell did. So he started with the continuity equation. Okay, and then we saw that, see, now if you can replace rho as epsilon naught divergence of E. This comes from the first Maxwell relation, right? The one that we derived from Gauss's law. And we saw that now if you add this term to the fourth equation, this as a whole, okay, J plus epsilon naught del E del T will always be zero because of the continuity relation. So that's what he did. So he added this extra term to the Ampere's law. Now, what is this telling you is that now if there's no J, okay, consider that there's no current density J. So then changing electric field will also result in a magnetic field. Okay. So that's how now both electric field and magnetic fields get, intertwined and connected to each other. And this epsilon naught daily identity can be termed as a displacement current JD. Okay. So that's how we reached to the the Maxwell's equations. And then whatever we did next was using the Maxwell's equations for various applications, right? So we went to the study of electromagnetic waves, where we know the typical expression for a wave equation, and we saw that if you start with the Maxwell's equations, considering that there is no free charge or current, okay, so rho is zero, z is zero, and then if you apply the vector algebra identities, you'd see that you'd get an expression like this, which is nothing but your wave equation. Okay, so that tells us that if you compare it with the typical wave equation, here it is telling you that you have a wave which is moving with a velocity, where the velocity is given by this value here, which is nothing but the speed of light. So this tells us that you can have electromagnetic waves in vacuum, and these electromagnetic waves are nothing but like it's like light. Okay, so light is an electromagnetic wave. So that's how we went to that conclusion. And then based on the different boundary conditions, you can now look at how the components are related to each other. And that led to a very important relation, which tells us that because light is a transverse wave, or electromagnetic wave is a transverse wave, there, like in free space, in vacuum, so there the electric and magnetic fields are always mutually perpendicular and perpendicular to the direction of propagation of your wave. Okay, and from the Maxwell's equations, you can actually relate the magnitude of electric and magnetic field by using this relations. If you know the electric field, if you know the medium property, okay, that is, if you know the speed of your wave in the medium, so then you can actually find the magnetic field magnitude using this relation. Okay. Because when you're having this wave that is propagating, it is carrying energy with it, right? So you can define energy per unit volume for the electromagnetic fields, and this is how the energy has contributions from both electric and magnetic fields, and they are equal. You can define an energy flux density, like it's a vector quantity that talks about what is the direction and magnitude of energy propagation, right? So you can actually, once again. Yeah, okay. So what we're currently trying to do is, this is like an extra session, which we thought we might be able to take. And like in this session, what we are trying to do is we are going through all the fundamental concepts that we had covered all throughout the course. Okay. So now we are talking about electromagnetic waves, where, it's telling you that if you have a wave propagating, you can define a pointing vector, which is given as E cross B by mu naught. So it's in the direction of propagation of the wave, and it tells us the it quantifies the energy flux density associated with the wave. Okay. Now this is for vacuum. For other mediums, your speed of the wave will vary based on the permeability and the permittivity of the medium, right? So mu naught and epsilon naught has to be replaced by mu and epsilon for that medium. Now, for a general, you can define a monochromatic plane wave by this general expressions, where, so suppose if you have a wave propagating in the z direction, then this is how your electric field and magnetic fields can look like. Okay, this is how they're related to each other. You can see that electric and magnetic fields are perpendicular to each other and also perpendicular to the direction of propagation of the wave. Okay, for a more general case, you can define the propagation direction by a vector, which is called the propagation vector or the wave vector k. Okay, so the spatial part that talks about the propagation is given as k dot r, as you can see here. And because it's a transverse wave, so if your polarization vector, which talks about the direction in which your field is oscillating, so that vector n cap should be perpendicular to the propagation vector k. So n cap dot k should always go to 0. Okay, so in a very general way, this is how a monochromatic plane wave with some propagation vector k and polarization vector n would look like. Okay, so these are all the different expressions for energy per unit volume. You can, try to find an expression. So because it is, so when you have this radiation going on, it carries momentum with it. So you can define the momentum of the wave. You can talk about how there's a change in momentum. Okay, and then you can associate it with some pressure. So that gives rise to this very idea of radiation pressure, which tells us that light can exert pressure, and that has huge implications when we talk about manipulation of objects using optical forces. Okay, optical forces can it like light can exert force on objects and move them and control their motion. So that comes from the fact that there's this radiation pressure associated with light. You can also talk about intensity of light, which is nothing but the average of the magnitude of the Poynting vector. Okay, energy flux density. So this is how it would look like. So if you know the magnitude of your electric field, you know that the intensity is proportional to square of the electric field amplitude. Okay, and it also depends on the medium properties. So for any other medium, okay, with some permittivity and some permeability mu, this is how your equations will all get modified, right? So the velocity of the wave will change, and this ratio of the velocities, will give you the gives us this refractive index. So when we talk about refractive index of a medium, this value has a measure of how the wave velocity changes as it travels through the medium. Okay, how different it is from free space. It's the refractive index is a measure of that. Okay, and this medium properties does affect the you know what do I say, the intensity associated with it, the current, how the energy is getting propagated, all of it. Okay, because it affects the velocity, it also affects the speed of propagation, it affects how the what is the energy density, all of it. Okay, and then even the boundary conditions would get modified based on the material. So if you have two medium with different dielectric constants, okay, because of the fact that you can always like when no free charge and no current is there, you can you can write the first Maxwell's equation as in terms of d, as divergence of d going to 0, which again tells us that the normal components of d should be continuous. And then for a linear medium, d is nothing but epsilon e. So that gives us this relation, right? This again comes from the fact that like when curl of E goes to 0. Again, here this comes from the magnetic fact that magnetic monopoles are not there. And this comes from the relation which talks about how the auxiliary fields are related. So when there is like from this relation, right? So all this different conditions. So if you have some net charge, surface charge, then this is how your, uh, you know, the normal components of D will be discontinuous. But if sigma goes to 0, then this would lead to this relation, right? And similarly the others. So So this is for the general case where you have some net charge density or current density, and this is the fact where you have no free charge or no free current. Okay. These are the boundary conditions. So this comes very handy when we talk about how lights propagate from one medium to another. What happens at the interface? What are the boundary conditions that need to be satisfied at the interface? So there, these boundary conditions become very useful. Okay. So when we did discuss about, when you move from one medium to another and there's a wave that is propagating, a part of it gets reflected, a part of it gets refracted. So what is the intensity of light that is getting reflected? What is the refraction, or the transmission intensities? So those can be defined in based on this boundary conditions. Okay. And from there you can define these coefficients called the Fresnel coefficients, which give us a measure of these quantities. Okay. So again, here what you do is you define general expressions of, waves. Okay. Incident wave, reflected wave, and transmitted wave, keeping in mind that when you're moving from one medium to another, your wave vector will change because the velocity of the wave is also changing there. Okay. While when the light is getting just reflected, or the wave is just getting reflected into the same medium, then only the direction of propagation of the wave will change. The wave vector or the velocity will not change. So accordingly, you start with the form of the, monochromatic wave, and then you put in the boundary conditions. Okay. And that gives you a relation that relates the incident amplitude with the reflected and the transmitted amplitude. And you can use them to find the reflection coefficient or the transmission coefficient. In an ideal case, R and T should go to 1, considering that there is no absorption. Okay. Now, when you have a conductor, some conducting material, and then light is propagating through it, then everything remains the same. But because of the conducting material, you do have a extra term coming in here. Okay. So there's a free current density that is coming because of the conductivity of the medium. So that comes in as a term here. So that's the only modification that happens. Okay. And because of that, what happens is your wave number now becomes a complex quantity. So where the real part talks about the propagation of the wave, while the imaginary part talks about the attenuation of the wave, which tells us that as the wave is getting propagated through the conductor, it gets attenuated. Okay. And that the reduction in amplitude, when it happens by a factor of 1 by e. Okay. So that's that distance is called the skin depth of your conductor. Okay. So for a typical good conductor, which has like where sigma is quite large, so there you can define your, attenuation of the wave by like this term here, like it's a simplified version of this. Okay. So you can see that this attenuation term comes in as this exponentially decaying term, while the real part talks about the propagation of the wave. Okay. So you can define, like any complex quantity, you can define an amplitude and a phase for your wave vector. Okay. And this is how it would look like. Okay. And then from there, you can also, now define many things. So what you can do is you can look at the ratio of electric and magnetic field amplitudes, and then define a wave impedance, which is a measure of what resistance the wave provides to the wave. The medium provides to the wave. Okay. So the wave impedance is given as the ratio of the electric field with the magnetic field. And this is how it would look like. It's a complex quantity. So that means as the wave propagates, new phases can get added. Okay. So now for a conductor, the electric and magnetic fields are no longer in phase, and there's a phase difference. Okay. And that would, uh, that would result in, as you can see here, so this ratio of the two, the imaginary part to the real part of the wave vector, will give you how different the electric and the magnetic field phases are. Okay. The magnetic field lags behind the electric field. And this term, this ratio here is called the loss tangent of your medium, because it also associates itself with the attenuation of the loss that your wave has as it propagates. So that was about, we discussed about the how we reach to the Maxwell's equations, and then how we use the Maxwell's equations for understanding propagation and transmission of waves in different media. And then what we talked about was what happens when in a circuit, when the connecting leads or the wires that are there, when they are when they start affecting the signal that is getting propagated. Normally, we consider that only the elements that are there will change the potentials or the voltages, right? We don't consider the effect of the connecting leads or on the transmission lines. But then under certain conditions, okay, we see that there is an effect of uh, the, the the connecting leads to the potential or the voltages or the signal that we are talking about. So when the connecting leads do not affect your signal, then it is a lumped circuit regime. While when it starts affecting, it is called a distributed circuit regime. Okay. So typically when it depends on the wavelength of the signal and the dimensions of the components or the wires that you're talking about. So when they become comparable, that's the regime where we have that's the transmission line regime where the effect of your connecting wires become like very what do I say, significant. Okay. So in those cases, one can do is one can define distributed parameters for the transmission line, where you break the transmission line into small unit cells such that each unit cell can be considered as a lumped circuit. Okay. And in each lumped circuit, so you will have R, L, G, and C. Okay. So basically, because you have two wires involved, you would have an associated capacitance to it. Because there's a current flowing through it, there'll be inductance associated with it. No wire is like of zero in resistance, right? So there's an resistance in the for the wire. And because of like the dielectric in between can have imperfectness that can result in a net conductance, basically a resistance in parallel. So all this are the different ways in which your transmission line can start modifying the signal that is getting transmitted. So each transmitted line is divided into small unit cells, where for each such unit cell, the dimensions are small enough than the wavelength of the signal that you can consider the unit cells to be lumped circuit regions, and there you can apply your Kirchhoff's law and all of that. Okay, so from there we get to these different relations, applying KVL and KCL to the individual unit cells of the transmission lines, which relates how the voltage and the currents are associated with the different distributed parameters. Okay, and that tells us that now when we solve for this differential equations, we get the solutions which tell us that now this voltage can be written as a sum of forward moving and backward moving waves. Okay, where the wave velocity is given by this relation here. So in the lossless case, if you put R and G to 0, you would get a simplified expression where it would be a very typical wave expression where the speed of the wave or the wave velocity is related to the inductance and the capacitance of your like transmission line. Okay, and you would have forward moving wave and backward moving wave. So like the general expression will be the superposition of the two. And similarly, now based on the impedance of your transmission line, okay, so you can define. So if the impedance is Z naught, then you can define the current accordingly. Or if you know what is the current that is flowing, so the ratio of the voltage to the current will give you the characteristic impedance of your transmission lines. Okay, so in the lossless case, we saw that is related to root over of L by C. Now, there can be different conditions that can arise. Okay, so in a very general way, you can start with some phasor representation of the potential, and you say that we know that the potential and the current satisfy the KCL and KVL relations. Okay, and from there, now you try to you get this wave equations like waves as the solutions. Okay, and where so if you have something like e to the power minus gamma z and then e to the power plus gamma z, then this gamma is basically the propagation term, okay, which would have information about the fact that your voltages can get attenuated, or there can be distortions or loss, okay, because of, so new phases can come in. Okay, so the imaginary part of your propagation term talks about the phases that can get added to your signal, while the real part talks about the attenuation that can come in, like the decrease in the amplitude of your voltage or current that can happen. Okay, so if so, what one can do is one can start with the forward wave, okay, and from there apply the KVL and KCL relations and try to find an expression for characteristic impedance, right? So this will be a typical expression of characteristic impedance for a transmission line of given distributed parameters. And then based on different combinations or different values of R, L, G, and C, you can have different situations. In such some cases, what can happen is that there is no loss. Okay. In certain cases, what happens is that the series time constant, which is given by L and R, are equal to the parallel time constant given as C and G, which depends on C and G. And then when they're equal, the lines become distortionless. So based on the use of your distributed parameters, that would govern what would happen to your signal as it propagates. And because you are having a wave that is propagating, so you can understand that now your voltage will be a function of how far you are from the, you know, like when you start from the source and you're gradually moving towards the load. So at different point in the transmission line, you would have different voltages, okay? Because of different phases that can get added up, different level of loss that can happen, okay? So this loss term alpha, you can define it in terms of dB per M and also or natural units as well. Okay. While the phase velocity is given by the beta part, okay, considering the lossless case, you would again get back the same velocity. Now we did see that, okay, so if you have a transmission line, there are like two conductors, and we can see the effect of the transmission line in terms of the distributed parameters. But now what happens when you have a termination at the end? So if you add some load at one end, there's a source at one end, there's a load at one end, and your transmission line has some characteristic impedance. So we saw that, based on the difference of the characteristic impedances, there can be reflection of the wave. Okay. So how much will that reflection coefficient be? So to understand that, you can solve for boundary conditions at the load end and at the source end. Okay. Considering that at the load end, your V by I ratio should be equal to the load impedance that is there. And from there, you can actually relate or define a quantity called the reflection coefficient that tells us that if your load impedance is different from the characteristic impedance of the line of the transmission line, there'll be a non-zero reflection that will happen. Okay. Similarly, you can do a boundary condition like solve for the boundary condition at the source. Okay. So at the source, so if you take your load as z equal to 0 point, and if your transmission line is of length L, then your source is at minus L, right? So then taking the common form of your potential, V naught e to the power gamma L plus V naught minus e to the power minus gamma L, that's the general expression of potential, right, on transmission line. Similarly, there's a current, just dividing the potential by the characteristic impedance, right? So from there, what you see is, this is interesting, that the physical understanding is interesting. It's telling you that in a transmission line, the effective impedance that is seen at the source is a measure of the length of the transmission line and also the load impedance. Okay, so if the characteristic impedance is known for the transmission line, but now if some load is provided at the load end, okay, and for a given length of the transmission line, it's this values, the load impedance and the length of the transmission line, that will affect the net impedance that is seen at the source. Okay. And we did discuss like concepts of, maximum power transfer and cases where, the impedance matching, why impedance matching is important. Okay. What are the conditions where the reflection coefficient will go to 0? Okay. the impedance has to match there. For we did discuss the condition of maximum power transfer where this concept of conjugate came up. Okay. So these were some of the things that we had discussed when we were talking about transmission lines. Okay. And the effect of transmission lines on signal transmission. So now based on what is the length of your transmission line and what are the load impedances, how different are the load impedances from the characteristic impedance. Okay, you can have all these different expressions for the source impedance. Okay, the general equation is this, and there were the different expressions, and we did apply it for solving many, uh, what do I say, numericals and all that. Right? We did see that, so this tells us that if you want to you like have a impedance match circuit, you can choose a combination of choose the length of your transmission line or the load impedance accordingly such that impedance gets matched at the source and the load ends. Okay, so you can use this for impedance matching and making like designing proper circuits. And then we also did discuss how waveguides are different from transmission lines. Okay, so while in transmission lines you can have TEM modes, in waveguides it does not support TEM modes. We rather have TE or TM modes, and that depends on the dimensions of your waveguides. Okay, so that came from the fact that here we again it started with the Maxwell's equations and then putting in the boundary conditions that the parallel component of electric field and the perpendicular component of V should go to zero on the inner wall of the conductor. And from there, what we saw is that these are the expressions that relate the different components of electric fields. Okay, so EX, EY, BX, BY are related to EZ and BZ. So which tells us that where Z is your propagation direction. So which tells us that if it's a TEM mode, EZ, BZ both are zero, so then there'll be no waves. So that tells us that any one of them has to be non-zero. So you either have TE mode or TM mode. Okay. And you can solve for TE and TM modes, okay, again by considering the separation of variables. And when making use of the boundary conditions, it's similar to how we solve for Laplace equations as well, right? The process is similar. The equation is different, obviously. Now here you have so this comes from the first and the second Maxwell's equations, okay? Putting in the explicit forms of the different components in the first and the second equation will give you these two uncoupled equations for Ez and Bz. And then by separation of variables, you can try to find an expression for Ez and Bz. There, what comes up is, so I'm not going into the details, but the main point is that waveguides act as high-pass filters. So there is a cutoff frequency, okay, below which things don't get propagated because below which your wave vector becomes imaginary. So it becomes an exponentially attenuated wave. Okay, so there's a lower limit to the frequencies that get propagated, and that depends on what modes are we talking about, okay, and what the dimensions of your waveguide is. Okay. And again, you can define the wave velocity and group velocity to it. You can visualize the same thing in terms of reflection. Okay, and the fact that there can be standing waves that can generate inside a waveguide. Okay. So that is something you can do. So this is a typical expression of cutoff for a given mode with a given dimension A and B of your waveguide. Okay, it again depends on the medium that is there. Okay, because there's a speed of the wave involved, and the speed depends on the medium or the dielectric that is present. So be careful about that. And then, so you can have TE modes where your is transverse electric. So then Ez is zero, Bz is non-zero, or you can have TM modes where Bz becomes zero, Ez is non-zero. Okay. And then putting the correct boundary conditions, you can define. So just as here, you could define an expression for Bz and for the different modes. You can also define an expression for Ez for the different modes and try to find the cutoff frequencies. Okay. We did look into planar mirror waveguides where you had two two parallel mirrors. Okay. where in the waves were getting reflected. They were undergoing multiple reflections at the two mirrors, and for proper transmission through the waveguide, one of the conditions was the self-consistency condition, which said that the wave should reproduce itself after two distinct, like two reflections. Okay, and using that, we led to this condition, which just tells us that the phase that it acquires when it makes two reflections should match with integral multiple of 2 pi so that it reproduces itself. And from there, we could get to the fact that there are some specific modes that can propagate through your waveguide. Okay, so again here it led. So this is the propagation constant that talks about what is the velocity of the waves that are propagating through your waveguide, and then based on this distance between the two mirrors, that limits what is the longest wavelength that one can have, or what is the smallest frequency that can propagate through the wave. So that again gives us a measure of the number of modes that your waveguide can support. Okay, so if d is the distance between the two mirrors, then if 2d by lambda is less than equal to 1, then what happens is there are no modes that are actually supported by the um, waveguide. So there's a there's again a cutoff frequency below which things don't get propagated. Okay, and this is a dispersion relation that relates the propagation constants with the frequencies of the signal. We did see that, just as having two mirrors and then air in between, that can act as a waveguide. You can also have multiple dielectrics of different dielectric constants stacked together. So if you have a core with a denser medium, and then you have clads with like cladding on the both side with which has a rarer uh, like smaller refractive index, like a rarer medium, then you can have, so based on certain modes, okay, such that you have total internal reflection at the interfaces, would ensure that you have propagation through this, planar dielectric stacks, and then it can act as a waveguide. Okay, so again, there's this self-consistency condition, which tells us that it should reproduce itself after two reflections. But here, because in the last case you had mirrors where the phase it acquires at each reflection is pi, which comes from the Stokes treatment as well. While here, because it's dielectrics, then you have to explicitly calculate for the phase that it acquires as it undergoes each reflection at the interface. Okay. And based on that, you can actually use the self-consistency relation to find the different modes that your waveguide can support. Okay, how much will this phase difference be? So you can get it from the Fresnel coefficients. So when you have waves incident and then reflected and refracted, you can use the Snell's law to find, what are the possible values. So here you do take into account the fact that your incident, the wave should be incident on the interface at an angle greater than the critical angle. Okay, and then based on the fact that now, because your angles can become complex based on the combination of your dielectric constants and the angle. Okay, so under those conditions, your reflection and transmission coefficients can become complex quantities, which means that at reflections, new phases can get added up to the wave. Okay, so just as we can find the argument for a complex quantity. Similarly, we find the argument for the reflection coefficient, and that's the phase that gets added up, and that satisfies this relation, right? So now, when this is included in the self-consistency condition, that gives us a relation that needs to be satisfied for the different modes. So it's a transcendental equation. So you plot the left and right hand side and see where they intersect. So those are the different conditions, different modes that are being satisfied, that are supported by the waveguide. Okay, and it's basically the ratio of these two that tells us what is the number of modes that can be supported by the waveguide. Okay, and here this very concept of numerical aperture of the waveguide comes in, which is dependent on this on the couple on the pair of refractive indices of the core and the cladding. Okay, and interesting thing is, like in the unlike the last case, for the mirrors below a certain frequency, nothing propagates, right? But here, because of this slight differences between the case of a dielectric stack and two mirrors, so here what happens is below a certain, you know, what do I say? This value, when this value becomes one, okay, that's the condition when lambda by 2d is greater than sine theta c complement. So in those cases, okay, there's one mode that is always allowed. So such kind of a waveguide can act as a single mode waveguide where only one mode is allowed to propagate through the waveguide. And that is given by this condition where you put m as one. Okay. And this would be your mode cutoff frequency. This is how to be related to the distance between the thickness of your core and the numerical aperture, which again relates to the different uh, refractive indices. Okay, so that's about the waveguides. So yeah, so to summarize, we started with electrostatics, then magnetostatics, then deriving the different Maxwell's equations, using it to understand propagation and transmission of waves, uh, and then moving towards what happens when you have uh, when the so an important part of electromagnetic theory is understanding how signals propagate, right? And their important point is in a circuit, if the wavelength or the frequency of the wavelength of your signal, if it is comparable to your connecting wires, then the transmission lines, it's the transmission line regime where the connecting leads now start affecting the signal. Okay, so we did understand how transmission lines work, how impedance matching can be made, how why important it is, and then how different a waveguide is from a transmission line. What are the different modes that can be supported in a typical waveguide? Okay, so all of that. In the next class, we'll talk about the about sources of radiations. Like basically, we'll talk about well, no, first we'll talk about different gauge transformations, why it is useful, and then we'll also talk about dipole antenna and how to characterize the field around an antenna and all of that. Okay, so that's about the next class. Thank you.